Collision theory and rate of reaction, part 1. So, collision theory, 5 major concepts. First of all, chemical system, as you know from grade 9, just consists of particles. They're always in motion, and the average kinetic energy of these molecules is going to be proportional to the temperature. In layman's terms, temperature goes up, average kinetic energy goes up. You guys see this every day. Think about a thermometer. Thermometer has some alcohol that's colored red inside a thin, narrow, encased tube. If you put your fingers at the bottom of the thermometer, you'll notice that the temperature goes up or the alcohol rises. Think about why that happens. When you put your fingers at the bottom of the bulb of the thermometer, you're increasing the average kinetic energy of the molecules. The heat from your fingers are making those molecules move faster and faster. And if you remember from grade 9 kinetic molecular theory, as those particles move faster and faster, they're getting further and further apart. So as they get further and further apart, the red alcohol rises in your thermometer to indicate that the temperature has gone up. So they're all related together. And if you're interested in hearing a funny story, ask me about Mr. Lumbee and grade 11 physics. So once again, as temperature goes up, kinetic energy also goes up. Second point, for chemical reactions to occur, there have to be collisions. And those collisions can be between particles, or it could be with the walls of the container that is holding those particles. Now, not all collisions are effective collisions. An effective collision has certain characteristics. One is that they have enough energy, and the second is that they have a correct collision geometry or correct collision orientation. These two factors need to occur so that the old bonds, or the bonds between the reactants, can slowly be broken, and then the new bonds, or the bonds between products, can start to be formed. Fourthly, if you have an ineffective collision, this just means that the particles are going to bounce back and remain unchanged, i.e. you're not going to form any product, everything is going to stay as a reactant. And for the fifth point, the rate of reaction is dependent on two factors. One is that there has to be an increase in the frequency of the collisions for the rate to go up, and secondly, that the collisions need to be effective. So let's take a look at a simple analogy. Our basketball player. For the basketball to go through the basket and score a point, two things need to occur. And the analogy will be that when the basketball goes through the hoop, then a reaction takes place and a product is formed. So first of all, your aim needs to be on. If your aim is off, you're going to miss the basket and there will be no reaction. So first of all, your aim has to be on. Secondly, even though your aim may be on, you have to have enough energy to get the basketball into the hoop. If you don't have enough energy, then you just throw up an air ball. And when you do that, no reaction occurs. So there's a simple analogy explaining why we need collision geometry and why we also need enough energy. So let's talk about this energy. We give it a special name. It's called activation energy. And we'll use a matchstick as an example of activation energy and what it is. First of all, your match doesn't spontaneously catch on fire. If it did, there would be trouble. To get the match to light, we need to supply enough energy to reach our activation energy. And we do this by striking the match against the side of the box. When we do that, we provide energy, friction, heat, to start the reaction going. Once the reaction starts, we all know that our match continues to burn. We don't need to strike it against the side of the matchbox anymore once it starts burning. So here's a question for you. Once your match has been lit, it continues to burn. So what can be said about the activation energy compared to the enthalpy of the reaction? And yes, we're talking about enthalpy and going back to our second unit again. Let's take a look at this as a diagram. Here's our activation energy and our enthalpy diagram that you should recognize. just a little bit different. I'm just going to grab a pen here. So we start off with our reactants. We've seen this before. Whoops. And then we also have our products, which we've seen before. The only thing that is different is we have this, I guess we can call it a hump over here, that's called our activation energy. This determines whether or not our energy will occur. We're going to take a very general equation. We've got a molecule of A, and we've got a molecule of B, and we've got our product, which is AB. Okay? So we'll take this step by step. First of all, our reactants are going to start to collide. As our reactants collide, bonds between our reactant molecules, in other words, our bonds between our A's and our bonds between our B's, are going to start to break. And as they start to break, new bonds are going to start to form. We haven't formed our product yet. This is just happening when the molecules are colliding. So what does that look like? We've got our A molecule, we've got our B molecule. As they bounce around, this is going to start to kind of form a very, very, very weak bond. And these might get broken a little bit. And we'll see how our reaction continues. As we go, so that's kind of like around this area, all the way maybe up to about here. Okay. So there we have a picture of our A bonds starting to break, our B bonds starting to break, and then this starting to form over here. Our activated complex is a highly unstable particle, and our activated complex is located right at the top of our hump right here. And it's a very, very transitional kind of complex. In other words, it doesn't stay around for a long time. It's very unstable, and it's made up of partially broken old bonds and made up of partially formed new bonds. So it's kind of like this, only these bonds here now become a little bit better formed and, let's say, a little bit stronger. So this is our activated complex. A little bit of A, a little bit of B, and a little bit of AB. If we have sufficient activation energy, then our reaction continues past the hump and we start to form our products. If there isn't sufficient energy, things will fall back this way and we will reform our reactants. And then we'll try it again. So activation energy is the minimum amount of energy required for a reaction to occur. If we have greater amount of energy than this bump, then yes, for sure they're going to go over the hill and down towards the product side. But this is the minimum amount that we need. And here we have our final new products that are formed. So when that occurs, these bonds are now broken. They don't exist anymore. And all we have is our bonds between our A atom and our B atom to form our molecule AB. So let's take a look at a couple of other diagrams. You'll recognize the diagrams. One of them is endothermic, one of them is exothermic. Hopefully you'll remember which is which. A couple of new points. Majority of our reactions that we deal with go in our forward direction, and that's the way we write it. But there is a whole class of reactions that can go either in the forward reaction or they can go in the reverse reaction. Ask me about a blue bottle experiment or demonstration that I can do for you that can show the reversibility of a reaction. Our delta H, same way that we did in our unit 2, is the difference between our reactants and our products in terms of potential energy. We talked about the activated complex of our forward reaction. EA is a short form for activation energy. The activated complex is right here, right at the very tip of our hump. And so in our forward reaction, our activation energy is from here and the beginning of our reactants. Note that our reverse reaction also has an activation energy, but it's a little bit different. Right? Because it's a reverse reaction, this becomes our starting point, and this is still where our activated complex is, much larger activation energy for the reverse reaction when we're dealing with, and this is an exothermic reaction. So let's take a look at their second diagram. We'll try to identify a few things here. Activation energy of our forward reaction. Well, forward reaction is always left to right. So for our forward reaction, our activation energy would be best represented by letter A. So this one here, letter A, is going to be our forward activation energy. Our reverse activation energy, I'll let you think about it for a minute, or maybe 10 seconds. You're right. Our reverse activation energy is letter B over here. So that represents our reverse activation energy. Our delta H, best represented by letter C. And hopefully you recognize this reaction as being endothermic, right? Our products have more potential energy than our reactants. We need to input energy into our reaction. And that is part one of collision theory and rates of reaction.